Guys, we're going to be working through an entire problem, exactly how y'all will need to work through it whenever you're working through a homework or a quiz or a test, as well as introducing the concept of statistical significance, right? So not only do we want to be able to find an answer, know how to kind of say how we found it and what that means, but we want to be able to interpret it as being either relevant information or not, right? So that's kind of the idea of statistical significance. So let's read through this problem. Before a blood drive, a local Red Cross agency puts out a plea for universal donors, hoping that they'll get more than the usual 6% among donors who show up. That day, they collected 202 units of blood, and among them, 17 units were type O negative, which is a universal donor. So the question is, does this suggest, so does that data that we found, 17 units out of 202, does that suggest that making a public plea is an effective way to get O negative donors to come to blood drives, right? So your first statement when working through these problems is going to be to state your question, right? So what we are expecting is, I expect 6% of all blood donors to be O negative. That should just be our blanket statement, right? Because we know that we have a usual 6%, right? We usually have 6% among donors who show up. So we want to decide whether getting 17 O negative donors among 202 people is statistically significant. Is this statistically significant evidence that the Red Cross's public plea may have worked, right? So I've written out for us your definition for what it means to be statistically significant, right? So our results will be considered to be statistically significant if it is not reasonable to believe that they occurred just by chance, right? So if we find that 17 out of 202 is drastically different, right? If this the probability of this happening is drastically different than that 6%, then we can state, you know what, this may be statistically significant. If it's too close, then we'll say, nah. All right, so let's work through this problem. Okay, so we've stated our question, and now what we need to do is to define our random variable x, right? So we're going to let x, our random variable, this is equal to the number of O negative donors. The number of O negative donors. Well, we need to check our conditions. If we want to apply maybe a normal model to this, which might be useful, we need to know whether or not it's a Bernoulli trial. So how do we know if it's a Bernoulli trial? Is it a Bernoulli trial? Well, we need to answer our three different conditions. Do we have just two outcomes? Well, our two outcomes in this case are whether they are universal donor or not, right? So our two outcomes is a yes, right? We've got universal donor or not. Universal donor or not. Excellent. Do we have a constant probability of success? Constant probability of success. Remember, P represents constant the probability of success, and in this case, yes, it's 6%. 0.06 or 6%. And are they independent? Well, does one person's blood type have an effect on another person's? No, it doesn't. So yes, we can say yes, independent. Okay, so we know it's a Bernoulli trial. So if it's a Bernoulli trial, then we can use a normal model if it passes two more conditions, right? So to be able to use a normal model, we need to know whether or not it passes our 10% condition, right? What is the 10% condition? We need to look at the total number of people who are donating blood. In this case, it's 202. And we need to ask ourselves, is that less than 10% of all possible donors? Is that less than 10% of all possible donors? Well, yeah, of course it is, because that's less than 10% of the population who are all possible donors. 10% of all possible donors. And the last condition that we need to check is the success-failure condition. The success-failure condition. And the success-failure condition states, hey, we need to have at least 10 successes, and we need to have at least 10 expected failures. To check this, we say, well, NP needs to be greater than 10, and NQ needs to be greater than 10. Well, N is 202, and you know what? I'm going to use a different color here for us. Let's do this here. We've got 202 for N, and our probability of success is 0.06. So hopefully that's greater than or equal to 10. And it turns out that that is 12.12. This is 12.12, which is greater than or equal to 10. Number of failures that we would expect to see, well, that's going to be 0.94 times 202, and that is equal to 189.88. So we would expect to see this many successes and this many failures. Since both of those are greater than 10, we pass the success-failure condition, and we've also passed our 10% condition. What we say after this is we are allowed to use a normal model. This is a statement that must be stated. Right, we got to say that. We go through, we check all these conditions, right? We show that it's a Bernoulli trial. We show it passes the 10% condition. We show that it passes our success-failure condition. So therefore, yes, we can use a normal model. Once we've done all of this, we can finally get into the mechanics of this, right? So to do that, we're going to need to be looking at our N value, which we already know is 202. We need to state what P equals, 0.06. We want to show what Q is, 0.94. And then we utilize all this information to find expected value, or mean, and standard deviation, right? So we know that E of X, which is the expected value of our random variable, that's equal to N times P, which is 202 times 0.06, which is equal to 12.12, right? So that is our mean, or our expected value. All right, and this is what we will be using in our normal model. We know how to find standard deviation of a random variable. That's the square root of NPQ, which is the square root of 202 times 0.06 times 0.94, and that is roughly 3.375, right? And that is our standard deviation, or sigma. Now, if we wanted to, we could go ahead and standardize this. Oops, sorry guys. We could go ahead and standardize this for whenever we write out our normal model. I'm okay if you guys standardize it, meaning you just treat your mean as 0 and your standard deviation as 1, and you find the z-score for the value that we found. Or you can just leave it like this, leave it in its normal units. So let's actually just go ahead and just leave it as is, and we can draw out our normal model with a mean of 12.12 and a standard deviation of 3.375. Okay, so let's draw this guy out. We've got our normal model with a center, right? A mean of 12.12. And we show, hey, we got a standard deviation up, 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 and then 3 of them down as well, right? So we've got 12.12, and I'm just plugging this into my calculator here, plus 3.375. And that gives us 15.495 for the first, 15.495. For the second, we get 18.87, 18.87. And for the third, 22.245, 22.245. Now, if we subtract 3.375, we get 8.745, 8.745, 5.37, and 1.995. Oops, I wonder if I can get this here. 1.995. And looking at this, we can probably pick out exactly where our data fell, right? Our data, we had 17 universal donors. So we already see that that is higher than we expected, right? If we know that we've only got 6% of the population is a universal donor, and we expect 12, about 12 to show up, but we got 17, maybe. You know what? Maybe that is going to be statistically significant, right? Well, how many standard deviations is that away from the mean? Well, looking at this, it's not even 2 standard deviations above, right? And we should be surprised by things that are more than 2 or 2.5 standard deviations above the mean. So, utilizing that information, right, we could look at this and we could say, well, the z-score of this, the z-score, and we find z-score by taking data point minus the mean divided by the standard deviation. We find that this z-score is only 1.45. Right? It's not even 2 standard deviations above the mean. So we can use this in our conclusion, right? So let's conclude. Conclusion. Although this is a very good turnout, although it was a good turnout, getting 17 type O negative donors is only 1.5 standard deviations more than expected, right? 17 donors is only 1.45 standard deviations higher than we expected. This could have just been random chance, right? This could have been or could have happened by chance. Right? If it had been more than 2 or 2.5 standard deviations above, we would have said, wow, this is really rare, or very unexpected, right? We wouldn't have expected to see this because it's so much higher than what we were expecting to see. That's whenever we would have been able to conclude, you know what, this probably did not happen by chance. I bet there was a relationship between the fact that they made this announcement. This plea probably did work. But since it's not, since it's less than 2 standard deviations above the mean, this could have just happened by chance. So, it's not strong evidence. Not strong evidence that the plea raised, scoot down here a little bit, raised the number of universal donors who came to the blood drive. Sorry that we have so much writing to do on this one, but with these kinds of problems, you know, there's a lot that you got to do. All right, we need to state what our question is, which we did up here. We stated what our question was. So what is it that we're looking for? Can we answer this question, right? So we answered. We looked to say, okay, well, we expect 6%, So we want to know whether 17 out of 202, we need to know if that is statistically significant, whether that's going to be evidence to show that the Red Cross's plea actually worked. So we stated that our random variable was the number of O-negative donors. We walked through, stated whether it was a Bernoulli trial, had to pass our conditions, the 10% condition and the success failure condition. Went on to show that we can use a normal model based on all that information and plotted this data on a normal model. Right? We showed that, yeah, 17, pretty good, but it's still within 2 standard deviations. So in conclusion, not very strong evidence, and therefore this is not statistically significant, right? This is not statistically significant. Statistically significant. Some beautiful handwriting there. All right, guys, let me know if you have any questions. I'll be around.